Welcome to a brand new series here at Trekzone. Yes, we're still doing it. We're into February now in our ambitious plan of 350 podcasts in 2021. This is all part of it. We now have 7 shows across the Trekzone network. This one, Talkin Science Interviews, is going to go in depth with the movers and shakers from science and space news. This week, I'm just going to bring up my chat with Professor David Flannery. He was part of the team helping the Perseverance rover in creating its mission parameters. And of course, that's very specific and very relevant because next week, Perseverance lands on Mars. We'll be going live for that landing. It's going to be absolutely fantastic. But Professor David Flannery is my guest on today's very first Talkin Science Interviews.
On Apple Podcast, Spotify, Google Podcasts, and YouTube for over 550 episodes. This is Talkin Science.
And Professor David Flannery is beaming in for a Trekzone conversation right now. David, thanks so much for your time this morning.
G'day, thanks for having me.
Now, Hayabusa is coming. We're gearing up to this coverage on Sunday of the sample returning to Earth. It's going to be landing in Woomera. OSIRIS-REx is coming as well. That tagged asteroid Bennu a couple of months ago. And NASA has the Perseverance rover on the way to Mars for a sample return mission of its own. There's so many samples coming back to Earth from across the solar system. In your field of Earth sciences, what does that mean for you?
It's definitely a really exciting time to be alive. I guess it's worth remembering that we have had naturally occurring sample return missions from many of these bodies in the past, including the rocky planets of the inner solar system and asteroids come to us in the form of meteorites. We're fairly sure we know where they're coming from, but to be able to go and get pristine samples ourselves really helps us peg our observations and test the hypotheses we've had for decades.
It really makes all the difference, doesn't it? Being able to go from theorizing about how stuff happens and how stuff works to actually being able to put the rocks under a microscope and definitively have answers to some of the questions and also probably create some more questions as well.
That's right. I mean, a lot of the meteorites that we have are altered on their way through our atmosphere and on the surface of our planet. And so when it comes to getting pristine samples of asteroids, for example, we can learn about the building blocks of the world that we know, life as we know it, organic molecules that were present before life evolved on Earth, also where Earth's water came from. And when it comes to Mars is a bit of a special case because we're able to test a lot of these ideas we have about the possibility that life evolved on Mars as well as Earth. We'll be studying these samples, I think, for decades, just as with the Apollo missions. Anything that comes back from Mars in particular will be studied for a very long time.
Now, you're born and raised in Australia, but you are working with NASA on the Perseverance rover as it heads off to the Red Planet. It's on its way, and it's going to be the first sample return mission to the Red Planet. How is that? What's that experience like to be able to know that you're part of a team that are going to be getting samples from the Red Planet back for the first time?
I guess the novelty does wear off after a while. These missions have a fairly long spin-up phase, about a decade. That's a short example with Perseverance. But you do have to pinch yourself every now and again and remind yourself that you are part of a much larger team that may look for or may even find evidence for a second genesis of life and hopefully get some of these samples back to Earth.
And I guess that's a little bit of a thing there as well with people in the public. And I've found this through the 8 years of podcasting that, we're on the outside looking into these missions that are very exciting for us. There's so much new stuff happening. But as you say, there's such a build up to these missions that it just becomes another job really for you. Just we're off to Mars. We're going to get another sample, but I guess when it sort of comes back and it's in your hands, it makes it all worthwhile in the end.
I mean, these will be the first samples anyone's ever returned from Mars, so that'll be monumentous, or monumental. But in terms of operating on Mars and sending hardware to Mars, after a couple of years of seeing objects the size of a grain of sand every day transmitted back from the Martian surface, it does wear off a little bit.
There still is that unknown of Mars, though, knowing exactly. I mean, I've just been working on my garden here in Brisbane for the better part of the weekend. It's full of clay, so very hard to dig into. We still don't we have an appreciation for what the soil is like on Mars, but there are still those unknowns, aren't there? Sticking a shovel, as it were, into the soil.
Yeah, there are lots of different reasons people want to get back different parts of Mars. The regolith is fairly well understood, and the dust that covers Mars has a global distribution and composition. But in the case of the Perseverance mission, we're going to investigate a package of really old rocks, really older than we've ever been able to investigate before. And that's significant because Mars in the past was very different to the way it is today. It seems to have been a lot more habitable, much warmer, a lot more water around, maybe a magnetic field to protect organisms from radiation. And so we'll be able to sample these rocks that represent this habitable time period, and we'll target those to return to Earth, looking for evidence of life. But there are many other reasons we'd love to get rocks back from Mars. For example, to date the surface. So we have relative age dates for the Martian surface based on the density of cratering. So the older a surface is, the more craters it should have. But we don't really have any dates to peg our relative dates to. So that's another reason we want to get material back. And there are many other people working on many other problems that each have their own samples they'd like to bring back.
And it's still only going to be a very small sample of Mars, isn't it? As we see here on Earth with different soil types around the planet, it's going to be the same thing on Mars. So this isn't the be-all and end-all mission, but it's certainly the start and a very exciting prospect to get those first looks at what Mars is like.
In some sense, that this is the most difficult part because we're trying to understand the context, the geological context, and take the best possible samples. And then to bring those back will be a technical challenge. But we want to make sure we've got the best possible samples first and we really understand what we're bringing back. Each sample we'll cache is about the size of a pencil. So not very large, but a huge amount of material with modern analytical techniques. You could spend a lifetime studying just a tiny part of that. And you see that with sample return missions to smaller bodies in our solar system, maybe interstellar dust, for example. You only need a few tiny little particles that people can really learn a lot from.
You know, I was fascinated about that, talking with Jason Dworkin from NASA Goddard about OSIRIS-REx, that it's only a couple of 100 grams of material that they've picked up from Bennu. And as you say, we don't need a lot these days to really analyse the inner workings of this soil sample. And it really makes it, I guess, it still is a massive technical achievement to get it back, but a little bit simpler that it's not a couple of 100 kilos of rocks.
Yep. And I guess it depends on what you're looking at. A lot of bodies in the solar system are fairly homogeneous. The surface of the moon is fairly homogeneous in terms of its composition, but there are reasons we might want to visit other places. So we got a lot of material back with the Apollo missions and smaller amounts with the robotic sample return missions led by the Soviet Union. But it turns out most of those samples may have come from a single impact basin. And so all of the dates we have for the age of impacts on the moon, which inform our understanding of the entire inner solar system and how easy it might have been for life to originate on Earth, could all be affected by the fact we only went to one place. And so there are lots of reasons to make sure you get the best samples from the places you really need to go. And Mars is a very diverse place. It's not all made of lava like the moon. We have, like on Earth, a huge diversity of sedimentary rocks and different elements that we'd like to bring back.
And can the samples returned give an indication of the best place to put a colony on Mars? Could it sort of work in that way, as well as looking at the history, looking to the future of the planet?
Perhaps. I guess the more we learn about the surface, the more we know about what it would be like to live on Mars. I'm a bit of a skeptic when it comes to the concept of humans living on Mars in a colony. I don't see any economic or political or religious reasons to do it. It'd be a very challenging thing to do. We will know more about those challenges as we better understand the surface.
Sometimes it comes down to a little bit of doing it because we can, which maybe isn't the best reason to do something.
Maybe not the best reason if it's costing hundreds of billions of dollars to get the first humans there, and much more to keep them alive in probably a fairly miserable environment, as far as I can tell.
Thinking about that, though, we would be able to get very specific rock samples and be able to shoot them back to Earth. So maybe there is something there. But
yeah, I mean, there's an argument to have humans on the surface because humans can get a lot more done than a lot of robots. But there is also the need to trade off the cost of a single human mission might cost probably well over $100 billion, whereas the Perseverance rover is a flagship NASA robotic mission with a price tag of about $2 billion. And so you could send 50 of those for the price of one human mission. If you think about how robotic technology is getting a lot better, autonomous systems are getting a lot more capable, by the time we have humans on the surface, we probably have some really capable robots that can do the job more efficiently.
Well, I know Mars is your bread and butter, David, but is there something exciting about Hayabusa returning in the next week, OSIRIS-REx in the next couple of years? China's also sending a sample return to the moon as well. Chang'e 5's on the way. We're getting all these samples back. Is there something exciting from not just Mars, but looking at these other missions as well to be able to study and analyze these rocks floating around the solar system?
Absolutely. I mean, in regards to the moon, people have been thinking about this problem that I just mentioned of how old is that really significant episode of cratering impacts on the moon and also therefore on Earth. When did that actually happen? We haven't known the answer to that question for decades. We've been poring over the Apollo samples, but they're really only from one area on the moon. And so the opportunity to get more samples back is huge for that community. They can test all of these ideas they've had moving around in the community for decades. And the same can be said for these robotic sample return missions to asteroids. We're learning all about what the solar system was like in its very early days. I mean, what was the Earth like before the age of the oldest sedimentary rocks? So on Earth, we can peer back in time with the geological record. We really stopped in our tracks at about 3.5 to 4 billion years ago, because that's the age of the oldest sedimentary rocks that we have on our planet. Our rocks get recycled because our planet's alive. This process of plate tectonics and weathering destroys them. And so we really don't know anything about what the Earth was like in the first 500 million years of its evolution, but that is preserved elsewhere in the solar system. These asteroids are 4.5 billion years old, and they contain the building blocks of the early Earth. And so it's an opportunity to learn about the early history of our own planet.
Fantastic, David. Well, looking forward to Hayabusa's return in the wee hours of Sunday morning. Looking forward to all these other missions that are happening over the next decade. Learning more about the solar system. Learning about where the Earth has come from, where we're headed. Even it's going to be a fascinating time ahead for geologists, astrogeologists, and everyone in between.
I agree. It's an exciting time to be alive.